Good morning, everyone. Thank you for joining us today for the PCI-SIG webinar, The Journey to CopperLink and Beyond, Exploration of PCIe Cabling Solutions. We'll get started here in just about a minute. Good morning, everyone. Thank you for joining us today for the PCI-SIG webinar, Journey to CopperLink and Beyond, an exploration of PCIe cabling solutions. Go ahead and introduce our speakers today. We have Sam Kocsis. He's Director of Standards and Technology with Amphenol, and also PCI-SIG's Cabling Workgroup Chair. We also have Mohiuddin Mazumder. He's a Senior Principal Engineer, Data Center and AI Division at Intel, and also serves as the PCI-SIG Electrical Workgroup Co-Chair and PCI-SIG Optical Workgroup Co-Chair. Now, I'll go ahead and pass it over to Sam to take us through the agenda and get started today.
Thank you, Kevin. So on today's webinar, we're going to talk about the motivation or need for cable solutions in PCIe applications. We're going to talk about PCI-SIG's journey to CopperLink, which will force us to look back through older cabling efforts that have taken place and some that are still going on in PCI-SIG today. We'll spend a good amount of time not only doing a brief overview of the 5.0, 6.0 CopperLink solutions and specifications, but also going into some deeper technical details, including some of the example methodologies to qualify the electrical performance of these cable links, talk about some of the sideband features and control plane mechanisms that CopperLink internal and external cables offer. And we'll go into some of the more recent discussions around expanding PCIe cabling from just copper solutions to also include active and optical cable solutions for 6.0 and beyond. So I want to start off by looking at a foundation for PCIe links from both a link width perspective as well as a data rate or speed perspective. So over 20 years of PCI-SIG continuing to double the data rate basically every 3 to 4 years. And that also includes expanding platform architectures to support wider buses and creating a truly impressive aggregate bandwidth between compute elements in platforms today. So PCIe links are defined as end-to-end, root complex to endpoint. And so when introducing cable assemblies, really any new interconnect solution, it's important to be specific about the performance and interface requirements for that portion of the link, which is why these CopperLink specifications are so important. It enables the platform designers to truly build out the full topology with the flexibility that they're going to need. One of the unique things PCI-SIG spec revisions build upon one another. Link training starts at slower data rates and then builds up to the max data rate that the system can support. So these systems will use often different implementations of reference clock and other control plane features. So it's important that the interconnect, whether a cable assembly or a connector, supports the transmission of those signals as well as the high-speed signals. You'll notice here in the chart that the 6.0 specification introduced a lot of new aspects to PCI link definition, things like new signaling scheme, encoding, some light error correction. But both the 5.0 and 6.0 specifications have a Nyquist frequency of 16 gigahertz, which creates a nice common data point to build from. So if we stick with that Nyquist frequency for a minute and look at the insertion loss performance of PCB materials over frequency historically, the key takeaway here is that despite material improvements, which have been made, as we go faster to higher data rates, the loss of the material is always increasing, making it more challenging to achieve the same physical reach from one generation to the next. PCI-SIG work groups have historically used an ultra-low loss material as a reference for their development. It's not the best material available in high volume or the worst material. But if we even include some of the newer materials that are in development, prototype for Ethernet, looking all the way out to even 60 gigahertz, the story is still the same. As the data rates increase, it gets more and more difficult to solve the problem using PCB solutions specifically. So that creates a need for cabling solutions. And the PCI-SIG has recognized this for some time now. There are currently 3 open work groups in PCI-SIG today. We have the cabling work group developing PCI Express external cabling specification. We have the electrical work group working on the CopprLink solutions that we'll spend a lot of time on today. And there's a new optical work group that was formed last August that's exploring different solutions to support optical PCIe links. In addition, there's the Oculink work group that has come and gone in that same time frame, working on a solution that attempted to cover multiple aspects of these solutions in one specification. We'll talk more about that a little bit later today. So if we think about this as a timeline, it's been about 20 years of development. Cabling work group opened shortly after the 1.0 base specification was released. These cabling efforts continue to work in parallel, trailing the base specification development for a number of years. The cabling work group was really focused on external cabling solutions, chassis to chassis. It changed form factors a few times, but has really remained a constant in terms of cabling efforts within the PCI-SIG structure. And then in 2015, the Oculink work group I just mentioned was formed. And this was really targeted at trying to combine internal and external cabling, as well as support for both passive and active or optical cabling, into a common form factor pinout that could be used across multiple platforms in multiple ways. And we've got some more, again, to talk about that as well. We have not forgotten about the Oculink work group. But in the last 5 years, the new interest in cabling is really sparked by newer platform architectures and applications that were created to support more disaggregated architectures. And that's really what's led to what's known today as CopprLink. And the combination of these cabling efforts in PCI-SIG is really marked by a requirement from system developers and users to align the platform performance and architectural expectations with form factor and physical requirements. If we look at the external cabling specification developed in the cabling work group, it's focused around the SFF 8614 form factor since revision 3.0 and beyond. I mentioned they changed form factors a few times. Our 1.0 and 2.0 specifications were self-contained with form factors defined in those specifications. Each of those solutions since 3.0 have really targeted a maximum reach of 2 meters within a single system. That's at the 5.0 32 gigatransfers data rate based on 30 gauge cabling. And the target applications for this would be something like an add-in card or a host bus adapter, really meant to align with traditional storage deployments for alternatives to SAS and SATA deployments. On the Oculink side, here's a few pictures to kind of highlight this single form factor, packaged and formatted a little bit differently, but largely meant to be a solution that could be a in-the-box solution, as well as an outside-the-box solution, with the provisions for power and control that would enable support for active cabling as well. And that was really targeted at PCIe 3.0 deployments. again with a maximum of 2-meter reach within a single system or to be used system to system. And that again was meant to expand upon some evolutions in the storage and data center server platforms that were looking to evolve at that particular data rate and time. Now, this is another way of looking at all these cabling efforts together. We combine sort of the date at which the specifications were developed, the last specification in terms of the base revision that they supported. All of these cabling solutions, although targeted at their maximum data rate, are meant to support data rates down to even the 1.0 speeds. Also talking about the maximum reach. At this point, all of these specifications of the numbers here are really normalized around a 30 gauge copper twin X solution. So that's a good way to frame the reference in terms of reach at a particular data rate and reach across the different specifications. And you can see the target applications have sort of changed. They've migrated from traditional storage applications into support for newer AI, ML, HPC type applications where disaggregated architectures and the need to support physical reaches are growing, as well as maintaining the higher speeds. With that, I'll turn it over to Mohiuddin to talk a little bit in more detail about the CopprLink solutions.
Thank you, Sam, and good day, everybody, wherever you are joining from. Thank you for your interest. And before I go, I also want to acknowledge this CopprLink work. It has been more than 3+ years of journey. A lot of companies and individuals and people contributed. Particularly want to mention on the cabling side, Amphenol, TE, Molex, Loads, Samtec, many of the experts contributed. Also, this work was under PCI-SIG electrical work group, and through the work group, it really needed expertise from silicon system and others, and the protocol side to get this whole work done. So I want to take that moment to acknowledge all who have contributed over a long period of time and made this specification possible. So as already Sam nicely covered some of the motivation behind going into this cabling solutions. So for CopprLink, which now covers 2 generations, PCI Express 5.0 and 6.0, and the data rate of 32 and 64 gigatransfer per second. As we go to such high speed and Nyquist frequency keeps increasing, it becomes difficult to go with PCB and longer reach, and also sometimes topological flexibility that are needed to innovate becomes limited. So that's created the urgency, and we started this development work. But as the cable provides us lower loss and longer reach, but low loss is not enough. In addition to low loss, we need to minimize reflection, crosstalk, and skew to develop robust cable solutions. We'll go over some of that. And it is an option to give more flexibility to the system designers and boost innovation. As you can see through the pictures here on the internal and external side, usually they are different applications in the sense that when it is external, shielding and radiation, all of those could be much more important, and overall modularity and robustness. So those are accounted for by the choice of appropriate form factors, as well as detailed mechanical and other. At the same time, there are some commonality that we try to leverage in both cases in terms of their electrical performance. So moving on to the next slide. So this is a quick summary of the internal and external cable solution. So as I mentioned, this delivers 32 gig and 64 gig data rates. The form factor for internal is based on SFF TA1016. This is a standard already published by SNIA, So we have a strong collaboration with SNIA in terms of that having a very matured specification. Similarly, SFFT 1032 was a new project in SNIA that was initiated in collaboration with PCI-SIG and also formerly known as CDFP form factor. In the internal applications, usually does not require as longer length. It's limited to max length of 1 meter. It's the specification. For external, it is currently specification is limited to 2 meter. Of course, longer can be supported with various cable options, but given the data rate and the Nyquist frequency of 16 gigahertz, specification details are provided up to 2 meters. We support both internal and external cases, the PAM4 signaling. That is where we have transitioned in 64 gigatransfer per second. It supports by 4, by 8, and by 16 configurations. And we have spent quite significant amount of time to reach consensus across the industry, how the sideband should be specified and what pin goes through what functions, and Sam will cover some of those details. And we have already covered that the new usages are coming every day, and we expect to see even newer applications that we may not have anticipated. So what are the objectives of these CopperLink internal and external cable specifications? So this is truly a collaboration between PCI-SIG and other standard bodies like SNIA and OIF. So in the part where PCI-SIG specification, it is focusing on the high-speed electrical specifications for 32 gigatransfer and 64, both the mated cable assembly as well as connector, based on internal SFFT 1016 and external SFFT 1032. We also specify the sideband functions, what the details will be covered, like some are basic, some are extended, and pin out for the high speed and sideband pins. The guidelines for 32 and 64 gig electrical spec compliance testings are given so that our best knowledge of how to do the testing and measurement of such high speed are captured as an informative specification. It is important to realize that these CopperLink specifications from the PCI-SIG need to be used in coordination with SFFT 1016 and SFT 1032, which then goes into more details for mechanical, material, environmental reliability, and other low-speed electrical specification. So combination of those specification provides the full comprehensive standards for this CopperLink specs. In the next two slides, I'm going to briefly cover that we call sometimes minimum PCI Express channel, because when we develop the base specification, in the beginning of the base specification, you basically have everything open. How do you define silicon specification, reference clock specification? How do you define channel specification? And cable falls into one of the component of the full channel. So we need to understand the interaction of all of those, and that is one of the reasons why Electrical Work Group sort of took this cabling initiative under its wing so that we can leverage the comprehensive understanding of all these interactions and still get the best of cable technologies. So if you look at in this slide, from 16 gigatransfer to 32 to 64, when we are NRZ signaling every generation, we double the speed, the Nyquist frequency went up, and that usually doubles the channel loss. But material and other improvements doesn't move as fast as the frequency dictates. So we went to the PAM4 signaling. So with the channel loss limitation, in this picture, you can see that we are going in a one connector topology or two connector topology, and going from a root complex to an endpoint. Sometimes we call it non-root complex. Even using ultra low loss PCB material, best quality, high cost, only about 13-inch routing is usually feasible at 32 and 64 within the loss budget. And that limits the possibilities that one can do. And wire cable now comes in, providing that flexibility. So if we look a little bit more, usually root complex could be representing servers, retimers, switches, and others. And endpoint often could be coming is in a CAM card. So the division of loss budget usually goes between how much root complex takes, how much the system routing and connector together takes, and how much the add-in card takes. So the next slide is for PCI 6.0, showing that breakdown of the loss budget. So system is taking 15.5 dB, 43%. That includes the vias, connectors, AC caps, and the routing, everything. Add-in card includes the non-root complex package, on-die silicon impact, and the routing, 8.5, only 24%. And the root complex could be a giant server package, and that takes 22%. So we had certain gap of 4 dB compared to PCI 5.0, which we then allocated that root complex, add-in card, and system all need to improve, not dramatically, but by 1 dB, and then 2 dB from the system, so we can still do that. So when you have such a stringent budgeting of losses, going into those traditional non-cable based will be very limiting, and that is the realization of the industry that we need to leverage the great advancements that have been happening in the cabling industry, some inspired by the needs in the Ethernet and other world as well. So in the next probably set of 4 to 8 slides, I will walk you through how do we develop new methodologies to quantify the electrical performance of cable solutions. We all want everything great, but the best performance also comes at a cost. So we need a methodology how we can get the optimal performance and also not sacrificing cost and manufacturability much. So cover some technical details of 2 sets of analysis. One is for reflection and one is for crosstalk. So for internal cable, usually we have an example here. There could be many such topologies, but as you can see, the cable takes it from a system board to a riser card. And then within the riser card, we may have multiple CAM connector or other connector-based cards. So that's, I call it 3-connector topology. It is great that this cable provides us extra length and flexibility to connect, but we need to make sure as it goes through multiple of those interfaces, other impacts such as reflection and crosstalk does not degrade the overall channel performance. Similarly, on the right side, it's an example of an external cable topology, which could be between 2 boxes, and there could be a long cable between those 2 boxes. So cable loss, depending on the cable R gauge, could be 5 to 10x lower than PCB loss. So it gives us a lot of flexibility that way. But we need to remember it mitigates the PCB loss limitations, but increases reflection crosstalk due to multiple interfaces, and that must be controlled to a level that we fully leverage the benefit of the lower loss. So this 3-connector cable topology, it is a highly reflective channel example. And what I'm showing on the right, that low reflection, high reflection from an intuitive thinking point of view, if you are in a sort of a beach which doesn't have many rocks, you will see it seems pretty quiet and pretty blue waters. But once you have a lot of rocks there, which will create a lot of surfs and high reflection example because of that whiteness. So that is pretty similar as we think of electrical signals moving on. It is like an electromagnetic wave. And every time it makes any type of vertical transitions or even in horizontal transitions, impedance changes, it is like a rock, and it is going to reflect. And it's going to reflect back and forth between multiple of those interfaces. And those reflection to a receiver is basically noise. And those usual SIM rocks and same interface changes also causes opportunities for crosstalk, and that also appears as a noise in our final receiver. So we need to control them. So an example that we are going to show that how do we come up with this specification, essentially answering this question. Because if I am the end user, I would like to get the best cable with lowest reflection and so on, but cable vendors and other keeps us honest that it comes at a significant challenges with technology and cost. So in this example, we basically took a half a meter cable, which is pretty common in internal cable applications, and then we vary the impedances of all of the boards, we vary their lengths, and then we look at what is the worst case channel. And then we will be studying for that worst case channel, how does reflection of the cable alone plays a big role. So what we do here in the next slide, we take advantage of a new metric that we have defined in the specification called integrated return loss. Again, thanks to our collaborators and partners who came up. It's basically takes care of the S parameter return loss, which is RL average. And then this weighting function essentially includes the spectrum of the energy that comes with the signaling. And then we also take care of the potential bandwidth of the transmitter and receiver. Those are dictated by the rise time. So using that metric, we can now look into that. For example, for this detailed S parameter return loss, corresponding integrated return loss value is minus 28 dB with a rise time of 25 picosecond. So we can then make this IRL number up or down and scale the S parameters accordingly to see what is the impact if I keep changing the return loss characteristics of the cable. Of course, here we do it in a way that S parameter still remains passive and causal, and insertion loss does not significantly change. So it's be careful with this application of such simplified metrics. But once you have that, then we basically generate those type of S parameters corresponding to different integrated return loss IRL values. And we perform a study. This study kind of shows here that we picked a particular topology parameters, which is on the x-axis you are seeing the trace impedance, add-in card length, backplane length, baseboard length, and then we vary the cable IRL scaling, meaning we are varying just the reflection characteristics of the. So you can see that once we improve it, higher means better return loss, lower reflection. It starts saturating, which means that if you improve it or even make it reflection free, there are other channel components which then take over. You don't get benefit from this cable component. So by doing those and making a judicious choice through the collective knowledge of the work group experts, we pick a number that is practical and doable, and then also feasible from enabling various interesting topologies in the system level. And we did that for 32 gigatransfer first, based on a lot of lab data and so on. And then we see to go to the double the speed, we need to improve it by another 5 or 6 dB. And that's how a specification is done. Okay. Similarly for crosstalk, and we look at that, how does the crosstalk of the cable alone impact? So we create models where we basically turn off the crosstalk of all other components. And then we vary the crosstalk, like near-end crosstalk and far-end crosstalk, and then look at how the crosstalk of the cable alone is impacting the performance, because we do not want the cable reflection or crosstalk to become a limiter for the end applications that we are looking for. So this is some details. And next slide, I will not take you through that much there, but we do consider foreign crosstalk. As most of you know very well, foreign crosstalk means the aggressor transmitter is far away from the receiver, victim receiver, and near end crosstalk when aggressor of the transmitter of the aggressor are closer to the victim receiver. So to have two physical origins, and we take care of both of them. So we do something very similar to what we have done in the reflection study. We take the crosstalk as parameters. In this case, for example, some of the original one is the red one, and then we scale that by 5 dB. Higher means crosstalk is increasing, lower means crosstalk is decreasing. And then we look at how those increase and decrease impact the overall channel performance by looking at the eye height and eye width. So this slide is basically showing that there's a lot of data here for you to review offline, but you can see that no crosstalk is when on the x-axis, we are basically choosing a certain particular topology. So what's the baseboard 1 length and 2 length, and the how much crosstalk scaling we are using, and whether we are enabling which type of crosstalk. So main thing to look at here is that if you basically look at any of those graphs, you will see that there are certain points when if you increase the crosstalk by more than 5 dB or 10 dB, you fall off a cliff. So we try to find those transition points and then decide that degrading further will be pretty disastrous. On the other hand, if we look on the left side, improving it a lot more will not really benefit much. So we do not want to overstress the stretch. So that's basically how we decides. So this hopefully give you an idea how the specification comes along with this collective work and detailed analysis. So I'll hand over here to Sam to cover the sideband details of the specification.
Thanks, Mohiuddin. Yeah, so we'll jump into the other aspect of these cable solutions apart from the high-speed interface, the control plane, or ways for the root complex to communicate and control endpoints on the other side of the link. PCIe applications aren't inherently peer-to-peer, so this control mechanism is extremely important in establishing a link and ultimately providing the flexibility for these cabling solutions to be adopted. So we'll start looking at the internal cable, although a lot of these definitions do apply to both internal and external use cases. This table here is a summary of the pin map for an internal assembly, the high speed, as well as the control plane signals. It's important to note that the internal CopprLink assembly is a purely passive cable with no power pins, no transmitted power, even locally to the connector interface. It does have connections on both sides that connect A to B. Every signal transmits from the cable on side A to side B. And I want to highlight the uniquely PCIe signals like PERST and PESTI that are included in the pin map, as well as the two-wire interface that's cabled across the link to help provide the remote management support. Additionally, users may choose to implement that control plane with a USB signal or even a by-one PCIe link. So provisions for these signals and their definitions are allocated in the FlexIO pins. So these FlexIO pins are flexible sideband usage. They could be configured for a number of different functions, and advertisement and discovery mechanisms are maintained at the system level. So these are discovery mechanisms that were introduced into the base specification, allowing the FRUs to talk to one another and establish that they understand how the root complex or endpoint or switch end are configured to make sure these pins and their signals are used appropriately. It's important to note that from a cable assembly perspective, these definitions specifically for the FlexIO at the system level have really no bearing on whether the cable is compliant or will work in the system. The cable assembly itself is wired again from A to B, and those FlexIO pins are going to transmit across from one side to the other, although they may serve a number of different functions depending on the application. Obviously, as you go from a by-4 plug cable assembly, you've got a certain number of high-speed pins available, as well as a certain number of sideband pins for use on those features on the previous slide. As you go to a by-8, the number of sideband pins available to you is increased. That could be used for bifurcation, by-8 to 2x4s, or providing an extended sideband use, additional GPIOs, or providing multiple control planes across the cable in an extended set. So this shows an example of how the internal cable assembly is wired from side A to side B. See specific allocations for where, if somebody were to use ref clock or the 2-wire interface or PESTI, you would have to use certain pin allocations. On the FlexIO side, there's a bit more flexibility, and the definition of what those pins would function as are included in the EPROMs that would be on either end of the FRU units that the cable assembly plugs into. On the internal cable assembly, there is no definition or EPROM in the cable assembly, but that is an important distinction as we look at the internal assembly versus the external assembly. We think about the extended use of sidebands. These are additional FlexIO as you go from a by-4 to a by-8 that are available to be configured. It's commonly expected that certain FlexIO would be used for optional use of specific key functions. And the work group attempted to establish what some of those functions were to try to drive convergence on, say, if you were to use USB, you would use FlexIO 7 and 8. So that way you'd limit the number of conflicts where a particular system on side A wouldn't be able to communicate or link up with something on side B. This again is a further pinout example of the by-4 fixed connector from the root complex side and the endpoint or non-root complex side. And then we'll go into the external assembly. And this is where it gets a little bit more complicated because unlike the internal cable, the external cable does have the ability to provide power to the module or the interface. It still has the same setup in terms of pin allocation. You have a high-speed portion and a low-speed control plane. In this case, there are a couple of signals that are local. The I2C, the SCL and SDA lines stay within the local port. The 2-wire interface and signals still transmit across the cable assembly to the other side. And you still have the allocation of flexible sideband pins that can be used for different functionality in different systems. One of the differences with the external cable compared to the internal cable is that these cable assemblies often have an EPROM inside of the module, which enable for advertisement locally at the port level, as opposed to having to do the advertisement and discovery across the entire cable. One of the other differences with the external solution versus the internal assembly is as you go from a by-4 to a by-8 to a by-16, there are some limitations with the number of FlexIO available. However, the work group established what the appropriate minimum set of functionality would be and made sure to provide provisions for those functions within the available FlexIO pins. And here we see there is some swizzling of the FlexIO definition on the root complex and non-root complex side, just to ensure that a differential pair could be transmitted appropriately with the right level of performance. So again, in terms of the by-16 external sidebands, there's a large number of additional flex I/O available for GPIO allocation or future use potentially. The by 4 and by 8 each have 4 sideband signals, and it's that core set of 4 flex I/O signals that the group determined were going to cover the majority of implementation requirements as far as definition for sideband pins that would need to be transmitted across the cable assembly. This is an example of that baseline set for the by 4 external cable connector and assembly, including power signals here. There's a 12-volt supply to enable some of the active circuitry that may go into supporting active or optical cables in the future, as well as a 3.3 volt for that EEPROM interface that may control some of the advertisement features for compatibility with other platforms and cable assemblies. This is additionally with the extended set for, this is flex I/O definitions, going into a little bit more detail about how the P and N are mapped to the root complex side and the non-root complex side across the end of each of the cables. This again just assures that a differential pair could be used if you were going to do something like a USB or a ref clock. You're able to get the correct configuration regardless of the orientation that the cable is plugged into. So there's no directionality in the cable assembly itself. And this again is another example pinout of the by 4 fixed connector. And these slides will be available to you. And I encourage everybody to, if you are a member, take a look at the CopprLink spec that's available to the PCI-SIG membership. It has a lot of these details in the full context of the specification and the way it should be implemented. So the last aspect of the control plane to cover that's unique to the external CopprLink assembly is compatibility with CMIS, or the industry's common management interface specification. This initially at a surface level is a agreed upon standard for formatting the memory map that would enable consistent communication between the host and potentially the other side of the cable assembly. It's come about in more recent years. Earlier cabling efforts in PCI-SIG had to create their own or adopt something that was introduced through another mechanism within SFF or another protocol group. Aligning with CMIS helps to, I think, enable many of the advertisement features that a lot of platform developers today are used to. It enables, specifically for PCIe, the ability to advertise the form factor that you're using, provide your PCI-SIG vendor ID, communicate that you are a PCIe compliant cable and which version of the base spec you may be able to support. It allows you to advertise the far end configuration of the cable. If you're a by 16 to 2 by 8s, for example, you can do that in an area of the EEPROM that's consistent across all users. And being able to leverage CMIS for this, there was not a lot of heavy lifting that the PCI-SIG or SFF had to do, and it creates an interface in a format that most users are familiar with. Specifically to PCIe implementations with the Flex I/O definition, this would also be a place where you can advertise if and for what you're using those Flex I/O pins for, as well as providing possible future placeholders for advertising certain things like optical link type, as these solutions could be extended to support active and optical cables, and attributes associated with those solutions like latency may be important to advertise to users that are trying to determine what's going on as they try to bring link ups and go through qualification. So it also enables us to utilize extendable upper pages of memory, unlocking new features that may be more critical and helpful as we expand this potentially beyond copper and into active optical solutions. So there's a liaison relationship that exists between the PCI-SIG and the optical interconnect forum. This is where the CMIS specification is being developed. So that's been helpful in making sure that both groups are aligned with the target applications for both sides and making sure that there's a path to creating a space for PCIe cables within the CMOS format. And so I saw there was a question about the compatibility of copper and optical solutions. And, so the opportunities, I think, for PCIe cabling here have really converged over the last number of years by the explosion of disaggregation, server platforms, as well as the emergence of interest in AI platforms. Traditionally, a lot of the cabling efforts have been focused on storage applications, but I think we're seeing more opportunities for using PCIe physical layer and PCIe cabling to support pooled memory applications adjacent to CXL technologies, and then possibly even extending the compute interconnect to create more of a fabric of networked accelerators and creating a GPU and CPU application link type that would really enable farther reach than what copper can get as we extend to higher data rates. So I don't view this as a separate solution if we're going to go from copper to optics. It really needs to be compatible. And a lot of the work that we're laying down with CopprLink, I think, is meant to enhance or steer towards that compatibility across the solutions. And just to find a finish on optics, we'll bring back Mohiuddin to talk about the optical cabling work group and what's going on with PCIe 6 and beyond.
Thank you, Sam. So hard to believe, it's almost a year. Now the PCI-SIG started an optical work group and to seek industry feedback in developing an optical interconnect. So the way PCI-SIG looked into it, that there are phenomenal advancements are happening in the optical, and goal of the work group is to basically make PCIe more optical friendly, somewhat in optical technology agnostic way, while we develop and continue to support PCIe needs, but keep the rooms open for all the innovations and various new technologies that are coming. So the form factors could widely vary. Some of the examples are pluggable and optical transceivers, onboard optics, co-packaged. The goal is to enhance the PCIe specification in a way that includes and more inclusive rather than choosing a particular solution. So we definitely invite, and we are very encouraged by the large membership that have joined this optical work group. We will continue all other traditional work groups like electrical and protocol because PCIe 7.0 is right around the corner in terms of basis specification. In collaboration with all other work groups, the optical work group will try to make the PCIe architecture more optics friendly. What it means right now is the focus is making the logical and other changes in a way that makes things more friendly to the optical technologies. So a lot of those details are being covered in the optical work group, and it has also an optical sub-team on the optical work group that gets into further details of form factors and various topologies that we will be supporting. So this last slide in terms of the status, it kind of shows, as Sam already described, the various usage scenarios. Optical is coming as an extension of our overall solution as PCI-SIG, enabling many different choices and components to make PCIe technology to go into myriad number of usage cases. What we show here on the right side is an example where we are calling it optical retimer. So this is where a logical enhancements are going to happen to cover a lot of those things that kind of break down from electrical to optical transition. But looking into the root complex and the endpoint, it basically abstracts things out so it can be implemented in a PCI 6.0. The currently logic subteam is focusing on what changes have to be made to make this particular solution work. And then it will take on that if we do not use retimer, how to make those type of solution work, starting with PCI 6.0 and 7.0, and on other potential options to reduce the latency and so on. So overall, many of these technical details are being discussed. I'll also point out in the recent last month, there's PCI US DEF CON conference, there was more details on how and what stage we are in terms of various changes. So please do review them and bring your feedback to the work group and then participate and contribute. So I think this brings us to the Q&A.
Yeah, great. So thank you, Sam Mohiuddin, for presenting today and providing your expertise. We did have a few questions from the audience here. And just a reminder to everyone, if you have any questions, please go ahead and submit those via the chat feature. And then any questions we don't get to today, we'll answer in a upcoming blog. So our first question is, I see, let's see. In your opinion, what absolute maximum for practically reachable Nyquist frequency for copper cable interconnection, for example, Twinax cabling? Or what is the absolute maximum for practically reachable Nyquist frequency?
Yeah, I can jump in, Mohiuddin, to start with this one. So obviously I'm affiliated with a cable assembly interconnect solution provider. We are exploring solutions even today for 224 gigabits per second and 448 gigabits per second with Nyquist frequencies over 100 gigahertz. We don't see anything in the cable twin-ax construction that would limit us. But obviously, as I started the talk off with, there's a challenge as you go to higher data rates in terms of being able to budget everything appropriately. You have to have a certain portion of the link dedicated to the package, the breakout, to get to that copper cable interconnection. And I think it's really about finding a balance that works all the pieces that's going to determine what the practically reachable maximum is for copper and copper cabling and PCIe applications.
I agree, Sam's your assessment.
Okay, great. Our next question here is, what is the projected channel loss budget for PCIe 7.0 specification?
Channel loss budget means die pad to die pad. It's minus 36 dB at 32 gigahertz.
Thank you. Our next question, how do you envision future optical cables to support sideband signals?
So there are two options that are being looked at. One is in-band. So it's basically a skip ordered set. So some logical changes are making its way through the ECN that we are working on that will allow the option not to use a real optical fiber to send the sideband, but it also does not preclude that if you want to use it through the optical fiber itself. So it's being addressed to provide an option to send the sideband through the in-band signaling. I hope this answers the question. Yeah.
Great. Our next question, does PCIe 7.0 architecture play a major role in AI or machine learning architectures?
Yes, we definitely believe so. I mean, because as we know, particularly with Gen AI and other applications, the demand for high-speed I/O and memory are extreme. So in that way, I mean, the industry is hungry for more I/O bandwidth, and PCIe 7.0 doubling that bandwidth again with keeping full backwards compatibility, we expect it to play a key role.
Yeah, I think even, I think going back to the target of this talk with CopprLink, one of the newer features here was to have this cabling effort be explored and evaluated underneath the electrical work group. And I think that alone helped drive better alignment between the base specification and the copper cabling solution. So I think with the 7.0 spec being able to leverage all of that, as well as potentially support for optical PCIe links as well, I think it has the opportunity to really be a major factor in AI architectures going forward.
Great.
And on that note, just want to add that PCIe Phi is also used in CXL applications. Many attendees may be aware of that. So once PCIe Phi and PCIe specification is done, it is used sometimes by other standards and other IOs. So it will extend its wing in that way as well. Yeah, go ahead, Kevin.
Next question. Do you think CopperLink has enough headroom for supporting PCIe 7.0 signaling, or do you need another cable specification for PCIe 7.0 cables?
So, we are already working on the pathfinding of 7.0. Electrical specification, I guess the question is whether the current form factor has the headroom. So those will be looked into. We believe that from an electrical specification point of view, a new specification, of course, will be necessary, meaning that we will need further improvements in performances, as we described, in scaling the crosstalk, scaling reflection, also getting even lower loss at double the frequency will require a new specification. But we will be open to looking into, more form factors that provides those benefits as well as the current form factors. So work group will basically continue to work with the aim that copper cable solutions as well as optical solutions, all of those keep making progress towards future high-speed IOs like PCI 7.0.
Yeah, I think there's a path to do that. And I think, jumping back here to one of the slides Mohiuddin showed, there's been a lot of work separately on the internal assembly and the external assembly. But this picture here even shows potentially a path to merging the internal assembly with the external assembly to create potentially a more optimized interface for the whole link. And I think a lot of these techniques will have to be explored, as we will likely need a new specification, as Mohiuddin said. I agree, but I think there's still a path for CopperLink and these form factors to support PCIe 7.0 signaling.
Yeah. Thank you.
I think we have time for one more question here. Given that the power is not passed over, how will the system cope with the timing of initialization for link training? The endpoint is effectively hot plugging, but this seems to be poorly supported right now.
Sam, you want to answer that?
I think this is one of the key aspects that we're working through with the concept of active cabling, right? Especially as we're looking at things not only as timing between the two sides of the cable, but potentially aggregating PCIe links across multiple ports of the cable. So it, I think this is one area where I think by having the cabling effort be explored and developed more closely in line with the electrical work group and the protocol work group, it's only going to make these issues that have been very problematic in the past hopefully get some relaxation and have a conclusion in the future. And if some of this can find its way into the compliance program, that I think has been a really nice feature of PCI-SIG's ecosystem, I think that'll also help alleviate some of those pain points that have been prevalent in the past.
I agree. I mean, any new learning comes, share with us, and we'll be able to address them. But we believe it will be still capable to use a lot of these features that PCIe has.
Great. Well, thank you both, Sam and Mohiuddin, for sharing your knowledge today. And thank you, everyone, for attending today's webinar. So these slides will be posted on the PCI-SIG website, and also we'll have the webinar available for on-demand viewing on YouTube and also here on Bright Talk. So for any additional information, please visit PCISIG.com. And thank you for joining today, and we'll see you at the next PCI-SIG webinar.
Thank you.
Thank you. Have a good day.